All right, so in the last section, we learned how to figure out antiderivatives. Right, and we did a lot of work. We got a lot of examples. You got hopefully fairly good with antiderivatives. But you might have left this section being like, all right, I mean, I guess I can figure that out. But that kind of came out of nowhere, right? I thought we were working on area below the curve, right? Wasn't that the problem that we were doing back in 3.1? And I'd be like, yep, absolutely. Right, back here in 3.1, we were really interested in figuring out, evaluating the definite integral. And as long as the curve that we're talking about was a straight line, then finding the area underneath the curve was just a geometry problem. We're adding up the areas of rectangles and triangles. But things got really complicated when the curve was, well, curved. Because we don't have a geometric formula that tells us the area underneath this parabola, for example. So we didn't have a way to figure out how much area was shaded in here. And what we learned is, well, we can estimate that area. We can estimate it fairly closely doing something like this, although I made the point that this won't be useful at all. We can estimate it kind of poorly using rectangles, which hopefully I hyped up a little bit is like the way to go. And the reason it's the way to go is because unlike this method, we can make this estimate as precise as we want by just changing the width of the rectangles. In fact, as I talked about in this kind of bonus episode, if we let the width of these rectangles get infinitely small, the algebra gets kind of insane, but we're able to calculate the exact area underneath the curve. And you're like, oh man, if this is calculus 2, I don't want to do calculus 2. This is absurdly hard. Figuring out the actual area underneath this curve, which I claimed was 6 2/3 units or 20 thirds units, was crazy hard. I mean, just look at this slide right here. It was wild. In fact, it was so hard that when we switched to this new section and started talking about something totally different, these antiderivatives, you probably didn't mind because you were like anything but the area underneath the curve. Okay, I got good news. You're going to really like this video because what we're going to do is we're going to go back and do that area underneath the curve thing again, but we're not going to do it that absurdly hard way by using approximating rectangles and letting those rectangles get infinitely small. If we're not going to do it that way, how are we going to do it? Well, remember, the way we asked the question, how much area is underneath the curve y equals 1/2 x plus 1 between 2 and 8, was by writing this group of symbols. The way we figured out how much area was there, which we calculated to be 21 by doing the rectangle triangle argument, was writing this. This looks a lot like these questions, right? We kind of have the same symbol. We have this weird little S looking symbol with a dx at the end. Here's the weird looking S symbol and the dx at the end. And then in between that weird S symbol and the dx, we had some stuff in here. We had an expression in terms of x that kind of looked like a function. That's the same thing we have down here. In fact, the only difference between the way we wrote the area underneath the curve, our definite integral, and these antiderivatives that we figured out in the previous video is we got numbers here and here, this 2 and this 8. I wonder if that means somehow there's kind of a connection between this idea, which again, to be clear, is the area under y equals 1/2 x plus 1. And when I say the area under, I mean below that line and above the x-axis between x equals 2 and x equals 8. Right? That's what this means. This means something totally different. Could not be more different, even though it looks really similar. This means figure out the antiderivative of this function. Right? And thanks to the last video, we can do that. Let's see, the way we figure out the antiderivative of this function is we bring the 1/2 out in front and then take the antiderivative of the x. The antiderivative of x, we think about this as x to the 1 power, so we add 1 to that exponent to make it x to the 2nd power. But that's not enough because if you took the derivative of x to the 2nd power, you'd get 2x, not just x. So I need a 1/2 out in front here. So there's this 1/2, but then another 1/2 to kind of cancel out this 2 when you do the power rule and take the derivative. This is the antiderivative of 1/2 x. The antiderivative of 1 is just x. If we want, we can tack on a plus c here to calculate the function that, if I took the derivative of that function, would give me this expression, 1/2 x plus 1. Could leave it just like this if you want, or you can clean it up a little bit and call this 1/4 x squared plus x plus c. Wouldn't it be awesome if somehow this was related to this? Well, it is, as you could probably guess by the way I'm saying all this stuff. How are they related? Well, the things that we're kind of missing over here are the 2 and the 8. The 2 and the 8 are the bounds of this area in the x direction, right? These are both x values, this 2 and this 8. They refer to this line x equals 2 and this line x equals 8. So what if, just for the hell of it, we took this expression right here, this antiderivative, maybe we give it a name like, I don't know, capital F of x, just so we don't get confused between this function and the function f of x equals 1/2 x plus 1, right? This is the function that we're looking for the area underneath, and this is the antiderivative of that function. So I'll use a capital letter so I don't get confused. Anyways, what if we decided to evaluate this function at 2? Because why not? We haven't done anything else with this 2. What if we figured out f of 2, capital F? Well, what we do is copy exactly what we see right here, changing all the x's into 2's. So 1/4 times 2 squared plus 2 plus c. Oh, okay, nothing too interesting here. 2 squared is 4. 1/4 times 4 is 1. 1 plus 2 is 3. So I get 3 plus c. I don't see how this has anything to do with 3 plus c. Don't give up just yet. Let's figure out f of 8, right? We've already figured out f of 2. Let's figure out f of 8 and see if anything interesting happens. All right, fine. 1/4 times 8 squared plus 8 plus c. See, 8 squared is 64, and 64 times 1/4 is 16. So I got 16 plus 8 plus c. I got 24 plus c. 24 plus c here, 3 plus c here. What am I looking for? Oh, right, the area underneath the curve, the definite integral of this function from 2 to 8. What was that? Oh, right, it was 21, right? Because I had this rectangle, which had an area of 12, and this triangle, which had an area of 9, and 12 plus 9 is 21. Is 21 at all related to 24 plus c or 3? You know what? 21 is exactly the difference in these two things. What a wild and wacky coincidence that if I took this 24 plus c and thought for some reason, I don't know why the hell I'd think to do this other than the fact that this kind of looks like this, thought maybe I should subtract 3 plus c. Well, let's see, the 24 minus the 3 would give me 21, and c minus c would just go away, and I'd be left with 21, which incredibly is exactly the same as this 21 right here. And you're like, oh, cool, good job. You made an example that just so happens that the area underneath the curve bounded between 2 and 8 is the exact same as the difference in the antiderivative evaluated at those two endpoints. No, I didn't do that. I didn't do that at all. What you just saw is what's called the fundamental theorem of calculus, and it is awesome. I can't express how cool this thing is. What it allows you to do is evaluate definite integrals. It allows you to find this 21. And you're like, yeah, no big deal. I figured out 21, no problem, by doing the rectangle and the triangle argument. Right, but remember how hard it was to evaluate this definite integral when it was a curve? That was super hard, right? We want a better method for evaluating definite integrals, and the fundamental theorem of calculus gives it to us. What it says is that if you want to evaluate this definite integral, all you got to do is figure out the antiderivative, capital F represents the antiderivative of little f, and evaluate it at these two endpoints. Evaluate it at the right endpoint first, and then subtract what you get when you evaluate it at the left endpoint. The fundamental theorem of calculus says that the definite integral from a to b of little f of x is equal to capital F of b minus capital F of a. A couple little comments here. It's important that these letters make sense. Little f is my function, capital F is my antiderivative. That's what I'm getting in this first point. The other point that I want to make is this only works if little f, is what that should say, is continuous on this interval. It only works for curves like this. It wouldn't work if like my curve looked like this and then jumped up here and did something like that and something wacky like that. Right? I couldn't figure out the area underneath this weird jumping curve. It only works if my function is continuous. But good news, we're not really worried about these weird jumping curves. All the curves we're going to care about are going to be continuous, so you don't really have to worry about that. But I, as a teacher, felt like I should point it out. One more comment, maybe this should be like point 3. There's really two different fundamental theorems of calculus. Sometimes they are referred to as part 1 and part 2, but that gets really confusing. So sometimes this one is referred to as the evaluation theorem. But good news, in our class, we're not going to worry about the other statement of the fundamental theorem of calculus. We're only going to have the one. So we don't have to worry about the fact whether this is part 1 or part 2, or whether we should call it the evaluation theorem instead. Technically, this is only half of the fundamental theorem of calculus, but we're not going to learn the second half for the purposes of our class because we don't need it in a business calculus class. So for our purposes, this is the fundamental theorem of calculus, and I hope you are very excited to see it. In case you're not excited to see it, let me do one more example. Let me figure out the area underneath the curve, pictured here, 3 minus 1/4 x squared, from 0 to 4. How much area do I have shaded in, where we count the red area as negative and the purple area as positive, and we net it all out? How much area do I have here? And before I do that, let me remind you of this. This is how we used to figure out that area. Do you ever want to have to do this again? If I told you that it's really important to figure out this area to get this answer of whatever it was, 20/3, do you want to do it this way? I'm sure you do not. I mean, I love math, and even I find this a little bit overwhelming. With that in mind, let's figure this out using the fundamental theorem of calculus. How would we do it? Well, we'd have to first figure out the antiderivative. The antiderivative of 3 minus 1/4 x squared is fairly easy to figure out. The antiderivative of 3 is just 3x. The antiderivative of negative 1/4 x squared, I leave the negative 1/4 alone. I think about my x squared. I want to add 1 to the exponent, so it becomes x cubed. But then I got to put a 1/3 out in front so that if I were to take the derivative, the 3 would cancel out with the 1/3 and I'd get back over to here. It'd be nice if I could put an equal sign right here, right? But I can't really put an equal sign because this is not the same as this, right? Really, the fundamental theorem of calculus tells me that if I take this expression and evaluate it at 4 and then evaluate it at 0 and take the difference in those two values, then I'll get this thing. So really, if I want to put an equal sign here, I have to write something like this needs to be evaluated at 4 and 0, and I need to find the difference between the two. It'd be nice if there was a mathematical way of saying all that, so I won't have to write it out in English. This needs to be evaluated at 4, and then also evaluated at 0, and then subtract those two answers. There is a way. You do it with a vertical line like this, and then you put a 0 here and a 4 here. That's it. Sometimes you stash some parentheses here just so it's really clear to the reader that this entire thing is going to be evaluated at 4 and then 0, and then you take the difference. That's what this line means. Some people even put one parenthesis on and use this vertical line as the closing parenthesis. I don't care how you write it. I don't care if you put the parentheses in at all, but you might want to get comfortable with this notation so that you can put this equal sign here. Before I evaluate this at 4 and 0, I'd probably clean this up a little bit. I'd call it 3x minus x cubed over 12, because 1/4 times 1/3 is 1/12, and 1/12 times x cubed is x cubed over 12. And then I'd make the point that I still need to evaluate that from 0 to 4. So let's first evaluate it at 4. 3 times 4 minus 4 cubed divided by 12, whatever that number is equal to. But that's not my answer. I have to subtract from that this thing evaluated at 0. So 3 times 0 minus 0 cubed divided by 12. A little bit low on room, but really it doesn't matter because this is going to be super easy. This whole thing is just going to end up being equal to 0. Over on this side, I got 3 times 4, so I got 12, minus 4 cubed is 64, so I got 64 over 12. And from this difference, I want to subtract. Let's see, 3 times 0 is 0, minus 0 cubed is 0, and 0 divided by 12 is 0. It's just 0. So my answer is just 12 minus 64 over 12. What's 12 minus 64 over 12? Well, let's see. These are both divisible by 4, so I could make that 12 minus 16 over 3. And then if I wanted to subtract these, I could call this 36 over 3 minus 16 over 3, and 36 over 3 minus 16 over 3. Whoa, that's 20 over 3. Amazing, huh? This is the same answer that we got when we did things this way and spent a whole page doing absurdly complicated algebra to get this 20 over 3. If you're not impressed by that, I don't know what to tell you. You should be impressed by that. That's pretty cool. That's so much easier than doing things the long way. The only downside with doing it this way is the why. Why does this work? Why can I evaluate a definite integral by looking at antiderivatives? And you know what I'm going to do here? I'm going to take advantage of the fact that this is a business calculus class and I don't need to prove results like this to you. It's not the most satisfying proof to show why the fundamental theorem of calculus holds. I'm just going to take this as a given. We've shown that it worked in these two different cases, right? We got 21 down here and we got 20 over 3 down here. It seems like it's working. Let's just trust that it works. Before I end this video, I want to make 2 more quick comments. The first one, when I took this antiderivative up here, you may have noticed, or maybe you didn't notice, I don't know, that I didn't put a plus c right here. Should I have? I mean, I don't know. I guess technically I should. The antiderivative of this thing should have a plus c here. But when I'm figuring out definite integrals, I'm always going to have these two different endpoints that I'm evaluating the antiderivative at, and then I'm subtracting. So if I put a plus c right here, well, then there'd just be a plus c right here, and then there'd be a plus c right here, and a plus c over there, and a plus c here, and a plus c here. And when I finally got all the way down here, there'd be a plus c minus a plus c. They'd go away, right? The c's are always going to cancel out. Because it would be the same constant over here and over here when I evaluate this antiderivative, they're always going to go away. So for that reason, when you're figuring out definite integrals, you don't have to bother putting the plus c in your antiderivative right here. If you're just being asked for an antiderivative like we were on this page, it's a good idea to tack on the plus c. But I can just tell you from experience, a lot of people forget, and it's not the end of the world. But technically, the answer to this question contains a plus c. However, when you're figuring out definite integrals, you don't have to bother putting a plus c in your antiderivative here because it's just going to cancel out when you evaluate it at the two different endpoints. The final comment that I want to make, that at this point I kind of don't even want to make,